Coming up on This Week in Space, Saturn has more moons. That relief mission is finally launching to the International Space Station. And when do we have our nuclear vessels in space? We've got Rob O'Brien from the University Space Research Association Center for Space Nuclear Research to tell us the tale. Tune in.
Podcasts you love.
From people you trust.
This is Twit.
This is This Week in Space, episode number 152, recorded on March 14th, 2025. Atomic Rockets 2, Nuclear Electric Boogaloo. Hello and welcome to another episode of This Week in Space, the Atomic Rockets edition. Can you put some reverb on that for me? I'm Rod Pyle, editor-in-chief of Ad Astra Magazine. Yeah, theremin time. And I'm joined by my babyface pal, Tariq Malik, editor-in-chief at the one, the only, the indispensable space.com. How are you, sir?
I'm doing well. I shaved this week, so that's why I look so like fresh and pink and and ready for the day.
Stop.
I also slept until 10 a.m. today, so it's all sorts of things, lounging around. So
wow, put that in the column of things we didn't need to know. And we will soon be joined by a fantastic guest, Dr. Robert O'Brien, who's the director of the Center for Space Nuclear Research, which is another initiative of the great University Space Research Association, which is at usra.edu. And the communications director there, Soraya, has been sending us a string of great guests, and we're very appreciative of that. Before we start, however, as always, please don't forget to do us a solid and make sure to like, subscribe, and do the other podcast things that will make us feel loved and make us popular so we can keep bringing you this lovely show because we're counting on you. And now it's joke time.
Jokes!
For which we occasionally have a sound effect, but today we'll make our own. There you go. All right. This is, I'm going to mangle this thing. There we go. Found the push button. This is from listener, and I apologize in advance for mispronouncing your name. I'm sure Jason Adamczyk, I think.
Jason.
Adamczyk. You know, when you get all those consonants clumped together, I always fail. All right. Hey, Tariq.
Yes, Rod.
Why was the Star Wars release order 4, 5, 6, then 1, 2, 3?
I don't know. Why?
In charge of scheduling, Yoda was.
Really?
It's a Yoda joke. I love it.
I like that one. Okay, let me try again. In charge of scheduling, Yoda was.
Oh, wow, that's even better. Oh, my God.
Now, I've heard that some people want to encase us in carbonite when it's joke time on this show.
You're really good.
You can help. Send us your best, worst, or most different space joke, as so many have, at twist@twit.tv, and we'll be sure to give you a call out on the air so that people can blame you for the jokes instead of us. Now, let's do some headlines.
Headline news.
Another sound cue there.
Headline news.
Don's staring at us like, what are you talking about? Okay, that's all right. We'll leave the Australian lady till next time. So finally, after months of, and I'm quoting here, stranded abandoned astronauts on the ISS, Crew 10 gets to go pick them up, which, of course, was in planning for a long time because these people were never stranded or abandoned. They were busy doing work on the ISS. And as I like to say every time this comes up, I have yet to meet an astronaut that doesn't say, I would love more time in orbit, not, gee, I really wish I could come home because my socks are dirty.
Yeah.
So tell us the story.
Well, yeah, this will be a real quick one, but we wanted to give everybody an update that NASA's big relief mission to the International Space Station to set the stage for the return of astronauts Sonny Williams, Butch Wilmore, as well as 2 other astronauts, will be launching soon as we are recording this episode. They're supposed to launch tonight on SpaceX's Crew 10 Dragon Endurance at 7:03 p.m. They are launching a bit late on this mission. They're supposed to launch in February originally. NASA pushed it to March because of issues with the Dragon spacecraft. It wasn't the one that they're using now. Endurance, the veteran of SpaceX's fleet, 4-time flyer. It was supposed to be a new version that apparently had some battery issues or whatnot, is what SpaceX had said. So they swapped that out. They're launching now. If everything goes according to plan, the Crew 9 astronauts, Sonny Williams, Butch Wilmore, may return to Earth on Sunday, May 16th. However, this launch was delayed from March 12th, which was earlier in the week as we're recording this. So it's unclear if that landing is going to get delayed. But the last I had seen, it was still the 16th.
So success
back on Earth at last.
Yes. And it'll be interesting to hear. And we will be having an astronaut on the show in the near future from not Butcher Sonny, but from that current crop.
Oh, we got to play our cards right, though. We gotta hope that all pans out. So,
well, if you're looking at me to be a card player, you're in trouble because I'm terrible at it. Now, from that uplifting moment to a less uplifting moment, the NASA layoffs continue. What the heck is going on?
Yeah, so this week we actually got word from NASA that in order to comply with Trump executive orders, as well as what I believe is DOGE workforce reductions, that NASA executed a reduction in force, an RIF, to shut down a few specific offices. So the Office of Technology, Policy, and Strategy is going to be shuttered. By the way, these stories are from space.com right now. The Office of the Chief Scientist, which is really strange, because we just have a chief scientist on board with Jim Green recently.
Yeah.
Really weird that they're going to close that office there. Because what does that mean for science?
It is worth noting he's a climatologist.
Well, yeah, there is that.
Might have something to do with it, but they're also shuttering that directorate.
Yeah, it's like the whole area, as well as of course the diversity, equity, inclusion, and accessibility branch of the Office of Diversity, Equity, and Inclusion. I guess it's a whole extra office because they're shutting all of that down from the Trump executive, the anti-DEI orders that Trump has put out. My suspicion is that a lot of these agencies had some kind of diversity or climate bent that the administration doesn't like, and that's why they're going to shut it down to try to save money. I didn't get a specific number about how many employees are affected, but it doesn't sound like it's like on the 1,000 list like there was before. So something somewhat smaller than that. But we'll have to wait and see how this affects science decisions and other missions in the future, not having these offices in place as they have to make decisions for budgeting, etc.
All right. And I have to just say, completely personal opinion, but shuttering the science directorate is just crazy because that's a pillar of what NASA does. It's what's kept them vibrant and relevant for years. And, you know, one casual interpretation without a whole lot of data points could be, hey, we just want to route all this money to Artemis and get people back to the moon. Then we'll worry about science, but that isn't what it really feels like. So it's hard to tell. All right. I know you're burning to do this one. Saturn is breeding. What's going on up there?
This is exciting. This is probably one of the most exciting space, like science news stories of the week. But a new study came out, and it turns out that Saturn has a lot more moons than we thought. So we thought that it had 146 moons. That's already a ton of satellites.
Yeah.
And what this new study that came out this week found out is that there are actually 128 other moons. So that's a grand total of 274 moons. That's a lot of moons.
So you know how
for
to
Saturn.
do math.
So I tell you, this is from space.com. That's why I can do it. I don't have to do the math, but it means that Jupiter, the king of our solar system with 95 planets, is now just like a meager wannabe when you compare it to the queen ring holder of our solar system, Saturn. So, and a lot of these were discovered by astronomers in Taiwan using the U.S., the Canada, France, Hawaii telescope, CFHT. It's out in Hawaii. And they found them all in 2023 by just, I guess, staring at the planet. I mean, who doesn't want to stare at Saturn, really?
Well, doesn't it seem unfair that Saturn already has the rings and it gets the crown for all the extra moons?
I know. I
mean, really.
I think that one of the interesting things from this study, though, is it is starting to bring up the question of what actually qualifies as a moon.
Right.
Because some of them are just super, super teeny tiny, like a few miles across. Whereas
so they're really like captured asteroids, maybe.
Yeah, and maybe are they ring fragments? Are they particles that just kind of found a stable orbit around the planet?
Of the Death Star that exploded.
I know. Saturn's rings, by the way, and one of the moons on Saturn is where an alien statue was discovered and sent a signal out in a sci-fi book. But
thank you for qualifying that. Wow, I thought we were going off at uncharted territory here.
No, it was they have like a like a detective / pilot person. Oh man, it's a good. I can't remember the author. I'll see if I'll see what I can do later on. But it's a great writer, Jonathan McDowell. That's who it is. So.
And I bet for our wrap up, you probably want to talk about the eclipse.
Yes, I do.
Which I missed because I was staring at the bottom of rain clouds.
Yeah, well, there was, as we are recording this last night, actually this morning, was the first total lunar eclipse of 2025. And it was visible across the Western Hemisphere. So if you lived in the United States, in North America, and South America, you got full-on coverage of the blood moon eclipse. I did not, because there were clouds over New Jersey right at totality, which is very frustrating to watch the moon disappear and then not get any payoff from it. But luckily the moon's still there, so it came back. Maybe my late night coffee ritual did that. But you can see all sorts of amazing photos at space.com, as well as wherever you get your news. And if you end up living in Asia or Australia, mark your calendars for September 7th and 8th. That's when the next total lunar eclipse will be visible to that hemisphere. And of course, every lunar eclipse accompanied by a solar eclipse. So in 2 weeks later this month, we will have a partial solar eclipse visible over really high bits of North America and Europe. And we'll be covering that too at space.com.
And it's a much bigger personal crisis when your solar eclipse gets clouded out than when your lunar eclipse gets crowded out, which is what happened to me last time. All right. Did you have anything else, or is that the package?
I think we could probably wrap it up there. I would say that there is a new billionaire that is entering the space arena. Eric Schmidt, Google founder and CEO, is now the CEO of Relativity Space, the 3D printing company, taking over from Tim Ellis, the founder and a USC alumnus. Fight on, Tim, to take Relativity Space into the next, the next level. They're building a Terran rocket. They announced that they're going to shift from that initial small rocket to the new Terran reusable rocket. This came from Space News, by the way, I think at Satellite 2025 conference this week, which is going to aim for a fully reusable medium lift vehicle. And then we'll see what their business model will be for that, to see like what their customers might be. So very interesting to see yet another billionaire after Jeff Bezos and Elon Musk and Sir Richard Branson jump into the fray. We'll see what Eric Schmidt wants to do, and then we'll take it from there.
When I become a billionaire, I'm going to do it too. All right. We will be back after the short break with Dr. Robert O'Brien, the director of the Center for Space Nuclear Research, to talk about, can I say it again? Atomic rockets.
Rockets.
Stand by.
Rockets.
And we are back with Dr. Robert O'Brien of the Center for Space Nuclear Research, where he's the director, doing some incredible work that was just a mere twinkle in our eye a few decades ago. So, Rob, welcome. Thank you so much for coming on today.
Thanks for having me. Great to meet you both.
Likewise. Now, you have a PhD in nuclear engineering. I got to read the resume because these things always knock me out. They make me feel about an inch tall. PhD in nuclear engineering and physics of radioisotope and nuclear power propulsion systems for space exploration from the University of Leicester? Is that how it's pronounced?
Leicester, yeah. Leicester. University of Leicester in the UK. Yep.
In the UK, okay. And a master's degree in physics and space science and technology. He holds several patents and patents pending and is a fellow of the Royal Astronomical Society. Sorry, my rundown disappeared for a second. You're an accomplished man, and this is the point at which Tariq and I usually do our big mea culpa about both having intended to have science degrees when we were in university, but we both met our Waterloo at differential equations and decided to become storytellers instead. So that's a fantastic background. How did that get you to the Center for Space Nuclear Research?
Well, that's a great question, and I'll just say, PhDs, masters, they're not the only route to success. Of course, there's the University of Life, which we're all on that journey for and through. So, my journey was through both an academic approach to study, and then focused on actual deployment and testing of nuclear systems, and that's what brought me out to the Center for Space Nuclear Research. I've spent a lot of time, a stint of my career in the Department of Energy National Labs, doing some pretty neat work and helping restart old reactors. And as we're doing now, restarting and regaining traction in some technologies that I think are going to be absolutely vital for human exploration and successful operations in both near space, cislunar space, and then beyond into the outer planets, and including exploration of Mars and the outer solar system.
I feel like we should, because we're here talking about propulsion and whatnot, that we should be calling you Chief O'Brien, like from Star Trek, right?
Oh God.
who kind of like was responsible for all the new advancements and all that, and here you are looking into what hopefully or what I guess logically would be the future of space propulsion later on. I have to follow Rob's question, Rod's question with my own, which is pretty much about the kernel of space for you personally. Like, is it something that you jumped into through your university experience there that really kind of grabbed you, or were you on a space kick well before that? What was kind of your first, I guess, inkling or exposure to space as something that was both a personal interest that would then evolve into a career there?
Yeah, great question. You know, I think for me, it started as a spark as a kid. I think it was probably growing up in the 80s and being a child of the 80s, that was really, there was a lot of space presence on TV and in movies. You know, Star Wars is a big driver in some of that inspiration, but also just growing up, you know, after the Apollo era, seeing the great accomplishments there, and then living through the space shuttle era, just how inspirational the science, engineering, and technology demonstrations were through those programs, and seeing it on TV as a kid, I think that was something long before I became a professional scientist or engineer. I knew I really wanted to work in space and help us get beyond what we're doing right now and what we were doing back then. And I think one of the first bits of engineering was probably model rocketry and amateur rocketry as a teenager that got me into being able to really understand not just the math or the equations and the models that are out there now, but actual practical experience. And that's what I'm excited about this next era of some of the work we're doing is really about deployment, testing, and really putting things into production now. So started at an early age.
Big model rockets, right? Big ones.
That's right.
Well, so I have a question about model rockets, if I may, because this tells us a lot about a person. Were you one of those guys that followed the instructions, or did you build them the way you wanted to?
I think I started following instructions, and I did things with my dad as a kid, putting models together, and he was a technologist and a professor in technology and electronics, and so I was able to do a lot of that learning from him. But then I started to put my own ideas into my projects as an older kid, and I started building my own designs, I suppose, and really going off the design or instruction sheet and thinking about why we need to do things and how we can solve problems. And that was also in manufacturing as well as just the assembly, so how to make new materials. I think composites as a teenager was something that I learned, and materials really became a focus then through some of my career. It's about making things, solving the technical problems, but the real materials behind those solutions is something that I probably started at that early age, heading off the instruction sheet and doing my own sort of innovating.
But to succeed, right? To succeed, right?
Yeah.
Not
Exactly.
Not to just see an explosion like some of my friends when we were growing up. So
Yeah, I take that personally. What was your involvement with the Idaho National Laboratory? They're kind of the eastern U.S. equivalent of Lawrence Livermore, right? In fact.
So I spent about 14 years at Idaho National Laboratory, working for the Department of Energy here in Idaho, and I was part of the Transient Reactor Test Facility, or TREAT reactor restart. That was the first reactor that went operational again since about the early 70s, since about 1974. And so we also, I led advanced manufacturing for the Idaho National Lab, again, focused on materials, trying to solve problems for general nuclear energy. And, now at the Center for Space Nuclear Research, really taking some of those experiences and connecting those as well as other capabilities at the other national labs in industry and in academia, which is really the importance of whole of government, whole of nation, being able to solve these problems and pulling them together to really engage these endeavors in advanced power and propulsion that we really need.
Well, that is awesome. But you're also, I mean, I guess there's other stuff that's going on at the center right now for space nuclear research. I mean, you're doing like the obvious research there, but you also have educational outreach and that type of thing too, to, I guess, get a new crop of engineers to take us to the stars.
Yeah, I mean, I think to quote some of my colleagues, space nuclear expertise is kind of unicorn capabilities and expertise at the moment, and we're actually working to resolve that issue. Talent pipeline for all energy, as well as nuclear energy in space, is something that we have to work as a nation to really push forward and develop. So at the Center for Space Nuclear Research, we do things differently to the traditional university approach to talent pipeline and talent development. We do things hand in hand with the programmatic needs, the drivers that are moving the development and deployment of nuclear technologies for space, hand in hand with the teaching and learning experiences for undergraduate, graduate, and then early careers staff, and then helping our center staff move the technologies forward. So it's that combination of all of the above that really drives success. And some of these technologies that we're talking about here push the envelope of materials and the physics that make it even possible. And so we think outside the box and redefine what the box is by working with the best, the brightest from around the world. And that's, I think, really an exciting avenue to work in right now.
I think we're going to jump to an early break because my next question is the meat and potatoes, and I want to have a clear flight deck for this. So let's go to a quick break, and we'll be right back. Stand by. All right, so the part that got me excited about having you on here is talk, and I grew up in the 60s, so I'll use the phraseology of the double features of the day, talking about atomic rockets, because atomic rockets sounds very cool.
Watch out, he's nuclear.
Yeah. So the big areas of investigation, as I understand it at this point, is looking at nuclear electric propulsion and nuclear thermal propulsion, both of which appear to be very promising for different uses because they have very different characteristics. And at least one of them is something that we researched quite a bit in the past, but maybe you could just sort of walk us through what the differences and advantages of those two kinds of systems are, if you would.
Absolutely. Yeah, of course, nuclear electric propulsion is something that can couple immediately with high TRL electric propulsion systems. The only nuance here is that we're generating electricity to feed those propulsion systems from a nuclear reactor or nuclear power source. And it doesn't just have to be a reactor, it could be a radioisotope system, which is 1950s technologies. And now we're trying to regain traction to enable 1960s technologies coupled to nuclear electric propulsion. And so some of the nuances here is that with nuclear electric propulsion, you can maintain steady propulsive operation and over a period of time build up a total change in velocity, or delta V, that could indeed leave the Earth's gravity well and go to the outer planets with electric propulsion. And there's different scales of power requirements for nuclear electric. There's robotic scale, and then there are power levels that push us towards exploration of Mars, for example, that could be enabled with nuclear electric propulsion that requires many megawatts of electric power. So whether we're talking about a robotic mission to cislunar space or human exploration to Mars, that's the nuance. That's the difference in power level. We actually believe there's a hybrid role between nuclear electric propulsion and an importance for nuclear thermal propulsion. And nuclear thermal propulsion is different because just like a conventional rocket, we exhaust a propellant through a nozzle, and that propellant, instead of burning it through a combustion process, we preheat it or heat it through a nuclear reactor itself. So just like we use water on Earth to cool a reactor, we use hydrogen or another propellant like ammonia or helium to cool that reactor. But in doing that, it too becomes a propellant, and we expel it through a nozzle, and that gives us thrust like a conventional rocket. The only difference is the efficiency is at least several factors greater than conventional chemical rocket systems. So the scale here is that we can have sustained agility and sustained maneuver with electric propulsion, and then agility for more impulsive needs using nuclear thermal propulsion. And so there is a hybrid role to play with both nuclear electric and nuclear thermal for all of the things that we're going to be doing in space, both for space operations in near space, cislunar space, and then to enable the exploration missions of the Moon and Mars and beyond.
But Rob, haven't we launched like nuclear? I mean, I assume that we're talking for these big propulsion systems, these big engines, like having some kind of a reactor on board the vehicle itself. Because you mentioned the RTGs, the radioisotope thermal generators. Did I get that right? Like the one that was on Cassini, the Voyagers, etc. And I know about those ones, but I feel like in the heyday of like the ramp up, the early decades of space exploration, we did as humanity send some kind of reactors into space, and so we don't see a lot of that anymore. And I'm curious, what experience have we, to have these kinds of, at least the reactors themselves in space, and then how do we need to evolve that technology for a future trip to Mars, etc. For these other missions there, because it seems like if we had that back then, shouldn't we have it now? I don't know how it works.
That's a story,
right?
That's both a sob story and it's also an inspiration point for us. It sets the bar of where we need to get back to with reactor systems. So to your question, we have flown a reactor system from the U.S. SNAP 10A as the reactor was flown in the mid 1960s. It was 60s. Successfully launched. Absolutely, and that's why I said earlier, reactors are 1960s technologies and radioisotope power is 1950s technologies. We face challenges with changes in policy and procedures and capabilities. I think the capability changes over the last few decades is what's a little concerning, but it's nothing that can't be solved with engineering and hard work. And that's what our community of practice is actively engaged in, is regaining that capability to build reactors and to sustain radioisotope power development. And despite some of the atrophy that we've had across the nation, we're working towards solving those problems. And of course, that requires investment, and continued investment. But the sort of return on that investment is incredible. What we can do when we regain the traction of being able to launch 1960s reactor technologies, and then pave the way to 2020s technologies that are going to allow us to maneuver without regret, to be able to move quickly through the regulatory space. That's always been a huge hurdle, especially for the commercial world. But as we look at in-space manufacturing, in-space propulsion, being able to generate propellant either on the Moon, Mars, or from near-Earth objects, that is going to be really important that we have these technologies. And so we've got to regain that.
So it sounds like, if I'm understanding right, in the 60s it was, can we do this? Can we put a reactor to power a spacecraft into space or orbit? And now it's like, what can we do with, I guess, 40 plus years, more than that, 60 plus years of technological advancement to make it work for us to get to Mars faster to power a moon base indefinitely, that sort of thing. Is that kind of where we're at in terms of technology development?
It is. In the Apollo era, the nation invested incredibly in several programs, and that to name a couple of them is the rover Nerva program that saw real nuclear thermal rockets tested to a significant technology readiness level, and to develop an understanding of how to operate those reactors on the ground, what kind of test infrastructure is needed to be able to do that. The regulatory space has changed, and we certainly will not test nuclear thermal propulsion systems in the future or today the way that was done in the 1960s or in the 1970s indeed. But we know that investment was made. We know what we need to do again, and so that sets a roadmap along with some of the study areas that have been performed over the last few years, where we need to regain traction in infrastructure. So rover Nerva was a great example, and then the SNAP program that involved both radioisotope power and fission systems, and actual flight testing under the Snapshot mission for a nuclear electric propulsion system. And the only reason that mission ended was absolutely nothing to do with the nuclear payload, the nuclear system. It was all to do with a voltage regulator on one of the payload systems. And so the system was safely shut down and put into a long-term orbit. We can do the same. And I think what's really exciting is moving ahead from those old technologies forward. There's ways to make the systems even safer than was tested, and higher performance than was tested in those early programs.
All right.
Just really quickly, if someone had a recovery ship, could they go and find that SNAP spacecraft then and restart it? Or is it like hard stops, like no one can crack it at all? If it's up there in a graveyard orbit, someone knows where it is, right?
Absolutely. There's a few expertise out there that know how to actually restart that system. It would require a rendezvous mission, like you suggest, probably robotic, or it could be a human expedition. Remember, now it's been several decades, so it's certainly cool enough from a radiological perspective for a crewed mission to go ahead and reattach some key components to make that system work again.
I'm just saying that there's tethered. Yeah, there's someone on this call who has effectively restarted a nuclear plant. But anyway, okay, Rod, go ahead.
All right, we're going to run to a quick break, and then we're going to come back to talk about one of my favorite stories briefly, which is rover Nerva. So we'll be right back. Stand by. So, Rob, you mentioned the rover and Nerva program, and it's a story I've been fascinated by since I was a kid, because we did have atomic rocket engines at one time that we were testing on the ground. And if fairly, I think by the standards of the day, a fairly threadbare program. It wasn't like they were throwing tons of money at it like they were Apollo, because Apollo was going to get us there now, and this was something for the future. But just to be clear, you kind of touched on this, back in the day in the 60s and early 70s, when they tested nuclear thermal propulsion, they did it in an area lovingly called Jackass Flats out in Nevada. And if I remember correctly, they'd pump up a cavern or a space behind the engine, and then start the reactor, and then let whatever I don't know if they were using hydrogen or xenon or what, flow through the reactor. And they tested it, but they tested it by blowing the exhaust out across Jackass Flats, which is something that you would absolutely not do today. So I'm presuming you have other methods to work on this, right?
Absolutely. So, yeah, they performed what we would call open air testing. The regulatory space was actually being defined as the technology was being developed back under the rover Nerva program. So, there was a lot of learning, and the lessons learned, and thankfully, new policies and environmental protection orders that were put in place for public protection. That's absolutely key to future development are now in place that mean we would not do open air testing.
Right.
Instead, we're actively working on key technologies to capture the exhaust, provide enclosures and full containment. So we have a source term holdup that is attributed to the system, so that even if the system catastrophically failed, there would not be a release to the public. We can protect them. And we do that with both containment, engineering controls, and then distance from the public. That's absolutely critical. There's only a handful of places to test, and certainly there's no decision on where the programs of today and tomorrow will be testing. But what we have to do is work towards those common goals in technology development while protecting the public. It's the public that want us to go to space and will ultimately benefit from human exploration and return of materials from space, and enrichment with life from systems and technologies in Earth orbit. If we think about satellite technology alone, that's improved the lifestyles of humans around the world and made the world a smaller place. And so that's why we do this. But we've got to remember that public protection is absolutely essential.
And just to kind of cap this on NERBA, I mean, it's a long story, but by the time they were done testing it, and this is with materials science, the state that it was in the 1960s, which has advanced a lot since then, they're running these things for hours as opposed to chemical rockets that run for minutes, correct?
Their tests were, minutes to hours in length, and so that demonstrates the endurance and agility of these systems, and ultimately the agility of a platform that could use the technology. Ultimately, cutting the mass required to propel a human mission to Mars to maybe 1/3 or better than would be required for chemical propulsion. But in doing the testing that was done under rover NERVA, although it was hours, it would be absolutely no different to what we're planning to do with nuclear thermal propulsion as we move forward. We need to ultimately quantify the margin to failure, and that is done through extended testing in prototypic environments, testing the nuclear systems, the subsystems, and how everything plays together that we need to learn, and ultimately work towards both robotic flight demonstration and then human exploration that will be enabled by human rating of an engine. So that does require a lot of testing, but most importantly, learning from those tests, doing the post-mortem analysis, what we call post-irradiation examination on nuclear fuels, to help us understand the margin to failure.
Rod found a great image of a NERVA engine on display. It's on line 51, John, there at the Marshall Space Flight Center rocket park. And I was just curious, because we talked a little bit about kind of the frustration of, having done certain stuff in the 60s, et cetera, and then having to relearn all of that. I'm curious what it feels like for you as kind of a scientist, pioneering this plan, to look back and see like that engine that they built, 60 years ago, and knowing that had we just kind of stuck to it, or at least, I guess, kept that focus where we could be, today. Because I've seen NERVA mentioned specifically in several recent sci-fi products, like sci-fi movies and TV shows, both animated as well as international, which was really exciting to see. But I'm just wondering kind of how that feels like, and I guess if at least seeing it in those sci-fi shows brings you some hope there about the support there.
Well, ultimately, these technologies are not just a good idea; they're going to be essential, and it's great to see that the science fiction world is also acknowledging the scientific facts of reality of space propulsion and power needs. So, it's exciting to see it, and ultimately, we need people to understand the technology, not be hidden behind some veil of mystery that it suddenly works. We need the public that ultimately for a public mission, or the commercial world that will ultimately sponsor these technology development areas, to understand what the technology is, why we need to adapt it and adopt it for deployment purposes, and then really embrace it, not be afraid of it, but actually with a little bit of knowledge about how these systems work, really get passionate about it and support the technology.
Yeah, I think if our listeners are interested, the NERVA instance that I'm thinking of was in Apple's TVs For All Mankind. There's a whole long arc about the testing of that engine on the moon, which seems like a safe place, Rob, that we can test these engines, right? Because there's no public to worry about there.
Well, that's right. It's the question is, how do you learn from the test, right? Mm-hmm. So we could do this in the depths of a really secure facility that was buried deep underground or on the surface in a containment with exhaust scrubbing, or you could do it on the moon. But you ultimately don't just want to turn it on. We don't want a binary answer: yes, no, it worked, or it didn't. We need to know the real engineering and science behind the material's capability to survive, the system ability to operate, and how long it can endure operation to understand that sort of margin to failure overall. So we have to be able to do the post-mortem analysis. And it's that infrastructure that engages both the sort of industry base, the national labs, as we talked about before. There's several national labs that have hot cells, but the journey between the test and the science that's accomplished in those industry and national lab bases and in academia is really what we need to focus on next. It's that infrastructure that's our next journey. So whether you test it on the moon or you test it in some new facility, you need to be able to take the engine apart safely and be able to package the materials and put them either over the road or on rail to some of these other facilities in a secure transportation package that can accommodate any kind of scenario that you might be concerned about from a safety perspective in transportation, and get the science done once the materials at the existing science base.
Well, and speaking of safety, and you kind of touched on this, but I think it's important to let people know, NERVA wasn't stopped because there was a disaster. It wasn't stopped because there was some massive problem with the technology. And it was operating on relatively slim budgets. I mean, when you look at pictures from the time, there's a lot of pickup trucks and lonely guys out there in an anti-contamination suit kind of dragging things around with ropes and so forth. But it was stopped because of the environmental movement and political concerns. Is that correct?
I think the real driver for stopping the rover NERVA program is because we did not continue on to Mars. Wernher von Braun knew that we needed to invest in nuclear technologies. In fact, at NASA Marshall Space Flight Center, one of our great collaborators, the team there on the Space Nuclear Propulsion Program and project area, have access to some hot cells there that were built by Wernher von Braun's team that actually knew that they needed to learn, needed to do the science to understand the margin to failure on nuclear materials and support equipment. So the knowledge was there, but that team didn't continue on to Mars at the end of the Apollo program. I think that's really why we saw the sort of demise of the rover NERVA program. I think it's a coincidence. There were other concerns with 3 Mile Island, and the way that the information was shared with the public, and really that veil of mystery created a shadow of doubt. And that's why, as we move forward, we have to educate. We need everybody that wants to work on this to understand and be able to communicate what the technology is effectively, so that there's no veil of mystery. There is a clear path forward.
And we're going to go to a break in a second, but just to terminate this part of the conversation, when we talk about, just in general terms, nuclear thermal and nuclear electric, we're talking about moving very large masses around deep space in a fraction of the time it takes with conventional chemical rockets, correct?
That's right. And probably the other detail to say is maneuver without regret. When we look at space operations, the regret comes when you make an unplanned maneuver, or you have to burn too much propellant, you leave nothing in reserve. That could lead to regret. So maneuver without regret is going to enable both Department of Defense, or Space Force, Space Command operations, as well as human exploration, robotic exploration, with margin to change and depart from the planned mission. I think that's what's really exciting about this, is this gives us the best chance to get people to Mars and bring them home quickly, to cut down on dose and radiation dose that people might pick up with a long duration transport and transit to the destination.
Okay, I'm going to get some T-shirts made up with maneuver without regret on them because I think that's a great term. We will be right back after the short break with Tariq's next burning question. Stand by.
Maneuver without regret, Rod, feels like nominal, like some kind of next gen space fan, mantra to keep around. I was curious, Rob, because you had mentioned how technology and systems have changed since the first inquiries or experiments with space nuclear propulsion, and one of the big talking points that Rod and I have talked about in the past is how will this up and coming, I say, investments in artificial intelligence and whatnot affect space exploration in general. Everything from helping cut down development time for new technologies to keeping astronauts sane on really long missions in space. And I'm curious if through your research at the Center for Space Nuclear Research with the USRA, where you see that AI technology falling in either the development of a future nuclear propulsion system or testing or modeling to streamline that process to make it either more acceptable to test on the ground or ensure more success when you do go to flight tests and that kind of thing.
Yeah, I mean, that's a really interesting emerging field and science in itself. I think whether we like it or not, science and engineering, commercial products, manufacturing, and then ultimately operation of systems, including nuclear systems of tomorrow, are going to have to engage in and will be engaging in uses of artificial intelligence, machine learning, and I think that's both exciting. It's not daunting. I think these tools can help us accelerate access to advanced materials, optimize manufacturing, and when we think about spaceflight, what we optimize for often is strength and mass for overall efficiency. And so if you think about optimization of structural components, as an example, AI, machine learning can help us design systems that are better from a mass performance perspective. But then if you think about controls, if you are looking at robotic missions or deep space missions that have a ground control element, the time to send a command, receive that command, perform an operation can increase, of course, the further away from that control center, if it's Earth-based. That will be a huge challenge for systems that respond quickly to conditions, whether they're nominal changes in power profile, power demand, or if there's an off-nominal event like a micrometeorite impact on a radiator panel, how does a system respond to that? Having a degree of autonomy that can control and close the control loop before a human signal needs to intervene, I think is both exciting and very promising. And then if you think about cybersecurity, if you have a system that is aware of its own limitations, shall we say, or has its own machine learning experience of where the margin to failures are, and understanding the influence of different actions that it may choose or the system may choose to perform, I think is really interesting, and it's very important because if there was a rogue signal, for example, asking a reactor to scale up to 1,000% power, the system knowing that that's not a good idea. Sorry, Dave, I can't do that. Hal's sort of response, I think, is probably where there's a good use of machine learning in the control strategy of tomorrow. So that's what we're excited about. USRA has invested a lot of time and expertise in developing quantum computing, machine learning, not just large language models, but also on the technology front as well. And I think that's where we're going to see a lot of use of these capabilities in the coming decades.
I think all the benefits of Hal without being a psychopath, right? So I think that's
exactly.
Good. That's good.
Yeah.
Yeah, and without the limitations of she who shall not be named, Alexa, misconstruing your commands.
Not Siri? Not Siri?
You just woke up my phone.
Oh, no, no.
I will get a lot of email and none of it friendly if I don't give you a chance to talk about the future potentially of nuclear fusion propulsion, and that was mentioned in some of the documents I was looking at. What kind of work is going forward with that? And if you don't mind looking into a crystal ball, because it's always been, to me, it's always been neck and neck with the conversation about boots on Mars. 20 years out, 30 years out, but it feels like we're getting a little closer.
It does, doesn't it? And I think that's because there's international investment in fusion science and technology that's been persistent over the last few decades. And ignition is one of the fundamental challenges with fusion. Sustained ignition, sustained fusion. How you fuel a fusion system of tomorrow, I think, is an interesting topic and thread to pull on in a moment. But I think if you just look at the types of technology, there's a lot of good investment there. I think generating electricity is one front. There's direct use of fusion for propulsion. And we all recognize that these advancements are going to come with industry and other investments from the governments around the world that are looking at fusion science. So that is going to help tomorrow's propulsion system. Today, of course, the focus is on nuclear fission and radioisotope power. We've got to accelerate the testing of those systems first. But in the background, there's a lot of promise for fusion for space applications, and indeed beyond just propulsion and power, how you can do science with fusion. For example, a neutron beam line of specific energies that can be derived from a fusion source. Space use of fusion energy in space may be coming sooner than many realize for interrogation purposes of, for example, on the lunar surface. If you want to understand the composition of some of the geology there, being able to explore and prospect materials, I think is going to be very interesting with both X-ray, gamma, and neutron sources. What we call neutron activation analysis is something that could be enabled with a very compact, electrically powered fusion system. So my crystal ball says we're going to need a lot of energy no matter what we're doing. So fission first, perhaps fission powering a fusion system to derive neutrons, or a combination of both, providing their neutron sources to explore fuels of tomorrow. And that's something that I think prospecting is going to lead to more energy enrichment of tomorrow, which is finding sources of fusion fuel as well as advanced fission fuel. Thinking about things like thorium on the lunar surface, we know it's there, and then helium-3 for fusion systems tomorrow.
I did want to kind of circle back, I guess, because we haven't talked too much about it, but you have touched on it, about the public concerns for all of this stuff, especially, like you said, getting stuff off the planet in the first place. Because I recall when New Horizons launched, to Pluto, that there were protests. When Cassini launched, there were protests, and I would expect that similar type of concern to come up. And there was a point where NASA was running out of fuel, and they restarted the process, and they were able to get it, at least for RTGs, for the future. And that's how we get Curiosity and Perseverance and Huzzah, years on Mars. But do you feel that now there is either more awareness about the care and the process that goes into it, or is that something that the scientists and the engineers that develop the next system to be tested in space will have to address through some kind of a public campaign of awareness and education to really lay things out in a way? Because it seems like there are more tools now to do that than there may have been for the previous missions, just from the breadth of news and social media types of ways to reach people.
Yeah, I think education is the key. The concept that in the vacuum of information, people create their own narrative, I think is an important remark to think on. So the science and engineering community, the teams in the government and commercial space that are going to use nuclear systems of tomorrow and in the coming months and years, as we see flight demonstrations take place, and all the work on the ground that will lead to those flight demonstrations, I think is really key. Is that we communicate with the public and not treat everybody as though they have no clue what a safe system looks like or what their concerns are about safety. People need to be understood about their concerns, and they need questions answered or information ahead of time provided so they can really understand and not fear what the science and engineering community is doing. And that veil of mystery that seemed to be the standard MO for how things were done in the past, with a smaller world, with the internet, with social media, no government organization or industry can hide behind silence. And so education is going to absolutely be part of the communication strategy as these systems move forward.
That's very well said. And as I recall, there was at least one unintended reentry, I think, by the Soviet Union of nuclear fuel elements at one point. But it's pretty well understood, certainly by today, of how to encapsulate these things into casks that are reentry proof and are not going to burst open in the atmosphere. Right?
That's right.
I think they recovered that too. I think they recovered the material from the sea in that one. Yeah.
All right.
There have been a couple of accidents where, the Russian Cosmos spacecraft came back. I think what's really important to say is for radioisotope systems, the systems are engineered for impact to protect the materials from being released to the public. And then fission systems of today and tomorrow are engineered so that they don't become critical. And that's some of the cutting edge work that we're doing, is that if they land on wet sand or are submerged in water, those systems are engineered not to become a critical configuration, that they fail safely. And that's really key. That's where the engineering has come along. Enabled by advanced modeling and simulation tools today, we can put systems together that we understand will be inherently safe through all operations.
Okay, well, so I've already expressed my fanboy predilections towards nuclear thermal propulsion, but there's one more area that I just can't wait to talk about, and that's Project Orion. Not the Orion spacecraft that's going to the moon, but Project Orion for the 50s and 60s, which was nuclear pulse propulsion, or atomic rockets, where you had spacecraft of various sizes that ejected small nuclear warheads out the back, and as those exploded, it pushed on this big shock absorber pressure plate. This is all in theory, and you could reach, according to Freeman Dyson, who was working on it for years and years, you could reach such velocities, as he put it, Mars by 1965 and Saturn by 1970, which didn't happen, of course, but I did write about this in a book I wrote a few years ago, and I think I called the chapter, or referred it to Barca Loungers in Space, because, I mean, they were talking about anything from the size of a very small unit that could fly on top of Saturn V to, and I had to check this about 5 times to make sure I got it right, 8 million ton, not 8 million pound, 8 million ton spacecraft, the size of Glendale, California, that would fly 150 people, potentially at interstellar speeds, and so on and so on and so on. So you don't want me talking about this because I'm not an expert and I get carried away. What are your thoughts on nuclear? Because studies seem to come back about every 5 years from various universities in Europe and the U.S. and the East, in Asia, about, this would probably work. It's icky to launch because you don't want to poison a bunch of people on Earth with fallout. But in terms of an in-space system, it seems like it would be a real breakthrough.
I think that's safe to say that there's very little to no interest today in launching a system from the Earth's surface propelled by nuclear devices. But for in-space, interstellar space, for example, there could be some rationale to look at pulsed nuclear detonation propulsion. And that's something that I think has to be looked at, not just from a back of the envelope or a calculation, but actually from a feedstock perspective, a chain of devices that can be effectively stockpiled on the system or safely stored, and then how you string those devices and operate them. I think that's challenging. And just remember that with spherical pulsed events, there's isotropy in where that energy goes. So when there is a pusher plate, for example, on one of these big spacecraft that we saw proposed under the Orion program, only a fraction of the energy that is generated by each device is actually captured on the system. So there's a lot of waste. At least 60% waste energy goes out to the other part of space. So it's only that momentum transfer between the device and the pusher plates that can propel us forward. So I think when we're really down to the wire on efficiency, there's lots to do with it. It certainly was tested with chemical explosives that pulse propulsion works by the Naval Research Lab. Actually, there's some videos on YouTube for anyone interested in seeing that. You can watch some of the old videos there where it was actually tested as a chemical system, not with nuclear. But I think it's an interesting concept.
Well, and for anybody who wants to look that up, it was called Putt Putt, which was very cute.
They also use the Orion nuclear engine in Sci-Fi's miniseries Ascension, which we've got a picture of that ship on line 65 there, John, as well as in Larry Niven's Footfall. That's what Rod and I were talking about this when we were planning the episode. That's how humanity fights back, is they build a giant ship and then launch it with an Orion pusher plate. They put the space shuttles on. It was like a big space aircraft carrier. It's pretty cool. So. But not the wave of the future, like Rob is telling us with the other engines. I think that these other ones sound a lot better.
He's damped down my expectations. Okay. Well, Rob, I want to thank you so much for joining us today for episode 152, which we like to call Atomic Rockets, with a big exclamation point and lots of reverb. Where's the best place for us to keep up with what you're doing and your various research and advancements?
Well, take a look at our website. It's usra.edu, and our center is csnr.usra.edu. Keep your eyes, of course, on the NASA Space Nuclear Propulsion Project pages and publicity information that's coming out. I'm really excited to see the continued investment by the nation in the program that will ultimately get robotic and human presence to Mars and the Moon efficiently, and give us preeminence in operation, I think, tomorrow. So keep an eye on those websites and of course the government program releases.
Go and say it to the mountain. Nuclear propulsion. Tariq, where can we find you reaching critical mass these days?
Well, hopefully not. I start with the trainer tomorrow, so we're gonna pare that bit back. But no, you can find me at space.com, as always, on the social medias at Tariq J. Malik. If you like video games, you can find me on YouTube at Spacetron Plays, where I have a whole video about the Blood Moon eclipse in both real life that we saw and in Marvel Rivals, which is a lot of fun. So I hope to see you there. And if anyone wants to hang out, let me know.
Just want to point out, Tariq, that I don't recall any of our PhD carrying guests talking about their video games on the show, but that's okay. And pursuant to that, listeners, if you want to drop us a line, you can do so at twis@twit.tv. That's TWIS@twit.tv. We love getting your comments, and one of us will answer each and every email. New episodes of this podcast published every Friday on your favorite podcatcher, so make sure to subscribe, tell your friends, and give us reviews. We count on you for your reviews. 5 stars or thumbs up will do just fine. And don't forget, we're counting on you to at least consider joining Club Twit in 2025. Besides supporting all the great programming that Twit does, you'll help keep us on the air and sending electrons your way about our great guests and my horrid space jokes. And it's only $7 a month. And as always, I ask the room, what else can you get for $7 a month, really? I mean, that's one fancy coffee at Starbucks, and some people do that every day. Finally, you can follow the Twit Tech Podcast Network at Twit on Twitter /X, and on Facebook, and twit.tv on Instagram. Thank you, Rob. It's been a real pleasure. I hope we can have you back. And
thank you for the time, Tariq. Yep.
Thank you, your Director of Communications, Soraya. And thank you, audience. And we'll see you next time. Take care.
For quick tech insights, dive into Twit's short-form lineup. From hands-on Mac, you can get helpful tips, great apps, and awesome accessories for your Mac, iPad, and iPhone. Hands-on Windows offers essential advice and everything new in Windows. Hands-on Tech zooms in on a specific theme with easy-to-follow advice that turns tech troubles into triumphs. Home Theater Geeks with Scott Wilkinson supercharges all things home entertainment. And if you like watching the shows, join Club Twit and you'll get full video access too, plus ad-free versions and more. Get informed fast with all of Twit.tv's short-form shows. Download and subscribe today on your favorite podcast player.